record on this computer. Right. Okay, so we've got a chat box here. I don't know why I'm having to admit people explicitly. I don't understand why people can't just enter. This is just so weird. So let's see. I think maybe the first thing I'll do is here I see everyone in. Okay, so, well, I think maybe since people are still coming in and since I've got to somehow admit them one by one, or at least I have to admit them explicitly, they can't just enter and I don't know why. I thought maybe I would review a little bit what's going on with the business of completeness. So let me just review that because it's kind of a long story. The first thing is that eigenvalues lambda are basically the minimum of the ratio of an energy functional divided by a norm, minimum over all u in, let us say, the domain. So twice differentiable, satisfying Dirichlet or Neumann boundary conditions. Then the second thing is that the lambdas are unbounded. So they just go to infinity as n goes to infinity. So the third thing is that if we imagine expanding a function, so suppose f of x is in the domain, so it's twice differentiable obeys boundary conditions, and we approximate it then by these eigenfunctions.
Professor?
Yes.
Can you click on the page? We can see what you're writing.
Yes.
Thank you.
Thank you. And I've got to admit somebody because this crazy thing about having to admit people, it's insane. Okay, so we're going to approximate a function in the f in the domain by a sum of eigenfunctions. And of course, you can see that using the orthonormality of these eigenfunctions, this function, this coefficient ck is an integral over the interval of the weight function, the function f, and the eigenfunction uk. That gives us the coefficient. The fourth topic was then that the norm then of Rn on uk is going to be 0 for k less than or equal to n. And the reason is that we've already included those UKs in the approximation for f. And so the inner product of the remainder with the eigenfunctions is 0. The next thing is that you can basically have that the n plus first eigenvalue is less than or equal to this inner product of Rn with Rn divided by the norm of Rn with Rn. And that's because the eigenvalue is the minimum of this ratio when you take into account all, in other words, it's over here, all U that are in the domain and that are orthogonal to the first n eigenfunctions. So this is something of a mouthful. I realize that. So the result of this is that n, the norm of this error, of this remainder, is then less than or equal to E of R, and I'm just rewriting this, divided by lambda n plus 1. So somebody else try. God. I tried to click on admit all, and yeah, geez. I'm really sorry about this business of people getting stuck in the waiting room. I don't understand. It used to be that you could just walk right in. Now, the next point is that E of Rn is bounded as n goes to infinity. And the reason is that E of Rn is E of FF, F being the function we're approximating, minus a bunch of coefficients, lambda k, ck squared, summed from 1 to n. And these guys here eventually become positive, and so this is less than or equal to EFF. Now we put all this together and we get 8, which is then that n of Rn, the error, in other words, is less than or equal to E of FF, which is bounded, divided by lambda n plus 1. And so that goes to 0 because the lambdas go to infinity. And then the final, that completes the proof of what we were trying to prove, but an additional statement is that one can actually show that this series, this sum of, let us say, ck uk of x approximating f of x, if f of x obeys Dirichlet or Neumann, God, another person I have to admit. I'm sorry about this waiting room thing. I'll get it fixed if it's possible to fix it before tomorrow's class. So let's assume that F obeys Dirichlet or Neumann boundary conditions, and that F prime is continuous, F double prime is piecewise continuous. Then this series converges, and like gangbusters, it converges absolutely and uniformly. We're not going to prove that, but mathematicians have, in fact, 100 years ago, I guess. Okay, I think that's enough for that. And now we can turn to nonlinear differential equations. I particularly like them, even though they're so very hard to solve. And what I like about them, or one of the things I like about them, is that because you can't just add solutions together or multiply solutions by constants, each solution has its own size and shape. And in the real world, things have sizes and shapes. They don't just have things. You can't just take something and multiply it by a constant and get another solution. And That, of course, means that finding the general solution to a nonlinear differential equation is even harder than finding a single solution. Now, fortunately, modern computers allow us to integrate nonlinear differential equations. And of course, one can, numerically at least, and so numerical solutions are available as long as one has finite numbers of degrees of freedom. Of course, in quantum field theory, you have infinitely many degrees of freedom, and numerical solutions are touch and go. Sometimes we get lucky. Here are two examples of exact solutions. I'll let you just sort of read them. Then one area where nonlinearity is important is in fluid mechanics. And for the moment, at least, I'm going to skip this equation, but it basically leads to, this section leads basically to Euler's equation and then the Navier-Stokes equation. And then there's something here on the speed of sound. I think it might be a good idea to do these tomorrow, if there's time in the problem session. Now, in cosmology, of course, you also have nonlinear partial differential equations, but it turns out that in many cases, they're a lot simpler than one would think. And in particular, what's been noticed by astronomers, I guess over the past 50 years or so, is that on large scales, the universe is homogeneous and isotropic in space, but not in time. And so the standard metric that was introduced by Friedman and Lemaitre and Robinson and Walker is this metric here that, and now what is ds squared? ds squared is the invariant distance between 2 points. In flat space, so let me do flat space. In flat space, ds squared is dx squared minus c squared dt squared. So that's the separation. And it's basically when ds squared is positive, so ds squared, this is space-like. And for space-like separations, things are either not interacting or fields at space-like separations, well, commute or anti-commute is what we say, but the functions of, oh God, what has happened here? Oh God, sorry. The functions of of quantum field theory become a lot simpler for space-like separations. Anyway, 2-point function, for example. Anyhow, here r, theta, and phi are what are called co-moving coordinates. So this is the ds squared in the this is the ds squared that's appropriate for very large scales. Here, A is the very important scale factor, and this is something that was very tiny right after the Big Bang, and then expanded, and it was about when the CMB, at the time of the CMB, A of t was something like 10 to the minus 3, and where we say that A of now is equal to 1. And this astronomers use 0 for now. Physicists tend to use a 0 for at the beginning. But since the beginning in astronomy has always been the most unknown, whereas in physics, the beginning is always the most known, the astronomers use a 0 for what they know, which is now. And so they set that equal to 1. The parameter k here, the parameter L is chosen, so the parameter k can be 0 or plus or minus 1. And so those are the three possibilities. K equals 0 corresponds to expanding flat space, and believe it or not, that's the best approximation we have. Okay, the space-like means that a signal, that in flat space, light signal can't go from one to the other. Time-like is when ds squared less than 0 is time-like. And there, a matter particle moving fast enough can go from one point to the other. And then ds squared equal to 0 is light-like. I guess that's the term, light-like or null. Some people use null. And that's how light goes. ds squared is 0 for light signals, always. The difference between coordinates and co-moving coordinates. Well, the idea is that in the co-moving coordinates, space is expanding this way. And so if you have 2 points that differ, say, in, let us say, phi. So the 2 points differ a little bit in phi. And then time goes by, the difference in phi needn't change, but the actual, in the co-moving coordinates, phi don't change, but the physical distance, so I'll write that in red. If the physical distance, let me switch to red. The physical ones look like this, then with the expansion of the scale factor, the distance will expand. Okay, so the physical distance, is A of, at any time, is A of t times co-moving distance. So that's the relationship between distances, and therefore that's the relationship of co-moving and ordinary coordinates.
Professor, I have a question. Why co-moving distance is not changing? Why it is fixed?
It's just the way it's defined.
Okay. Thank you.
So anyway, by the way, this, in the chapter on general relativity in my book, this is not on page 1. This is on page 60 or something. So feel free to ask lots of questions, and also in the chat, use the chat also to ask a question. It's easier for me to read the chat than, because the sound isn't always great and I'm hard of hearing and so forth. And anyway, Friedman wrote the equations for this kind of a homogeneous and isotropic universe he boiled them down to two equations for the scale factor. One is for the acceleration of the scale factor, and the other is for the squared velocity of the scale factor. And now you see this second equation here has been just an extraordinary simplification, because you start out with general relativity, where you have completely nonlinear partial differential equations, and from the point of view of actually solving them analytically, it's a nightmare. Of course, at least it's classical. Quantum general relativity is then something could drive one insane. But Friedman boiled this all down so that when you have space homogeneous and time just affecting the scale factor, you get two equations, and one of them is first order. So a first order equation, I mean, we've learned how to integrate such things. And here, rho is the energy density, K is that thing that's 0, 1, or -1, and then A is again the scale factor. I've kept the speed of light, which was actually very hard for me to do, to keep the speed of light, because most people drop it, set it equal to 1. And when I do physics, I pretty much always set C and H bar equal to 1. And so it's very hard for me to put them back in, but I went to the trouble of actually doing that. The other Friedman equation is independent of K and is the second derivative, but it's a second order differential equation. But at least it's an ordinary differential equation. And these equations become even simpler when the pressure and the energy density are related. And when you also use conservation of energy, and now a simple relation between the pressure and the energy density basically only happens when the energy density is due to a single constituent. So for example, right now, as far as we know, something we call the energy of empty space, or dark energy, is the dominant form of energy. And in the future, we believe, according to the latest cosmology, dark energy will become more and more important as time goes by. And so in another 10 billion years, the universe will be mostly dark, almost entirely dark energy. But in the very beginning, close to the Big Bang, the universe was mostly radiation. And for about 50,000 years, it was radiation. That's my memory. At around 380,000 years, the radiation cooled down to about 1 eV, which I forget what that is in ordinary temperature units. But anyway, it was cool enough for hydrogen atoms to be stable. And at that point, photons could simply go through the hydrogen gas without being scattered. And the universe suddenly became transparent. And those photons then that came from the originally terribly hot universe and have been traveling ever since and slowly being redshifted, they form the cosmic microwave background radiation. Conservation of energy, this is explained again in chapter 13, gives us that rho dot is -3 rho plus p over c squared, a dot over a, dot being time derivative. And then if you know what p is compared to rho, in other words, you have an equation like this, you can then write rho in terms of A0. Well, once you have, rho in terms of A. And then where rho 0 is the present value of the energy density, and A0, of course, by convention is set equal to 1. You can then rewrite these equations in a much simpler form. and they look like this. And so these are Friedman's equations for a simple universe. In other words, a universe in which the energy density is all either radiation or matter or dark energy. In reality, of course, it's the sum of all three, possibly some fourth thing that we don't even know about. And of course, when I say matter, I mean ordinary matter and invisible matter, which is unfortunately called dark matter for historical reasons. That's what a German astronomer working at Caltech called it. Although he was writing in German, I think he called it Dunkelmaterie or something like that. So there are, maybe we can do these examples. Suppose we have a universe dominated by a cosmological constant. So this is the dark energy case. Empty space, in other words, it has an energy, and that's all the energy in the universe. In this case, this parameter W is -1, and Friedman's equations become quite simple. And if we now set lambda equal to 8 pi Newton's constant, energy density, present day energy density, and we assume that this is actually negative, which is kind of crazy, and set k equal to -1, then the scale factor satisfies this harmonic equation, and what you've got is an oscillating universe. And then this, if you integrate this equation, you get these, you get this solution where lambda is squared is given by that. And then the magnitude of alpha, this parameter here, is speed of light over 2 lambda L, where L is that parameter that I mentioned, that for k equal to 1 is, and our actual universe is huge. It's at least 10 to the 3rd light years, 23rd, I'm sorry, 10 to the 13th light years. So let's see, where was I here? I'm sorry, we were in the Dissider case. So here we have, then with an initial condition of A0 equal to 0, we get the scale factor goes as a sign. So this is a pretty crazy universe, and this is called Antidissider space. Turns out there are no k equals 0 or k equal 1 solutions for negative rho 0. On the other hand, if we take the case that seems to be true, we have lambda, Newton's constant obviously is positive. The energy density experimentally is positive. Now the scale factor obeys A double dot is lambda squared A, and obviously lambda squared is positive. We get these exponential solutions, and so for k equal to 1, we have the scale factor expands as a hyperbolic cosine. K equal -1, it expands as a sinh. And k equals 0, it can either expand or decay exponentially, but and of course it could be a linear combination of those. Let's see, can it actually be yeah, k is 0, and so we have a very simple, this becomes a linear equation, so this can be a linear combination here. So maybe I should say something about that. 506 equals 0 case. And these represent the same maximally symmetric space-time known as Dissider space. That's one of the things about general relativity that can be confusing. namely that one of Einstein's ideas, one of his many brilliant, correct ideas, was that we should be able to use any set of coordinates we choose to describe physical reality. And so the equations have to be tensor equations such that when we change coordinates, we get back the same equations. It's just the same equations in the new variables. And in this particular case, these three solutions represent in different coordinates the same space-time, which is known as de Sitter space. So this is de Sitter space is where you have a positive vacuum energy, which is the present case, and anti-de Sitter is the crazy case. Okay, there's a question here. Are the different values of the equation of state defined or calculated? Well, the deal here is that I would say they're guessed at more than defined or calculated. The deal is that you can calculate if it's radiation, W should be a third. If it's matter, W should be approximately zero, in the sense that the idea here is that the matter particles aren't interacting. So that's why it's not, 100% theoretical. And dark energy, as far as we know, W is -1, but and that would be true if if it's just the energy density of empty space. But of course, we don't know the actor, so we don't really know. So this is an approximation for this. Certainly for matter, it's an approximation. For radiation, it's you can calculate that it's 1/3. It's done in chapter 13. You can calculate it's 1/3, but again, even that's an approximation, because what we're talking about with radiation, it's exactly 1/3 if we just have photons and other massless particles. But if we have particles of all kinds of different masses and different energies forming the radiation, then W is not really 1/3. Okay, and of course, we don't know beans about dark matter or invisible matter. All we know is it doesn't interact with light. And also, it hasn't interacted with any experiment that we know about, apart from a mysterious possible observation in Italy. But most people think that there's something wrong with that experiment. Anyway, figure 7.4 plots the absolute value of the scale factor. And so here's the way it looks. This is the absolute value of the scale factor. So for the crazy case is anti-de Sitter, and then it just sort of bounces around. The de Sitter case looks like this. And so let's read the caption here. Lambda greater than or equal to 0, k equal to 1. That's the solid case. So our real universe, by the way, if we look at our real universe on a scale, in fact, on the scale in which gigayears go from -100 to +100 gigayears, our actual universe could well be described by this solid curve approximately. This is the point of view of a bouncing universe, which is it was put forward by Steinhardt, if I'm not mistaken. I think that's his name, Paul Steinhardt at Princeton. Then if you have positive energy density, positive dark energy, and k equal -1, you get this dashed case. And the dotted one is anti-de Sitter, which, as I said, it apparently isn't isn't reasonable as far as we know. By the way, the present value of the dark energy density is 5.9 times 10 to the minus 27 kilograms per cubic meter. That may not seem like a lot, and it's not a lot, but we're talking empty space, and there's a lot of empty space. So this adds up. A universe of radiation, then you have W equals a third. The Friedmann equations look like this. You can set R to the fourth equal to this. I'm just defining R to the fourth to be that. Then the K equals 0 Friedmann equation, this one here becomes A dot is R squared over 2. I don't know why I used R. That was a stupid use. So let me do 7.507. I think R was silly because we really think of R as a radial distance. Anyway, what you get is A dot is R squared over 2A. So that's 2A dA is R squared dt, A squared is RT. And so the K equals 0 solution for a universe of radiation is just very simple. It goes as the scale factor grows as the square root of T. In our universe, we can pretty much ignore this 1 over L squared. And so that's a good approximation during the first 50,000 years of the easy era of radiation. The K equals plus or 1, minus 1 solutions are a little bit different, but as I said, for practical purposes, one can set L equal to infinity, and then you just get back, and then you can forget about whether K, the value of K. Experimentally, the physical observations of astronomers and physicists indicate that K is experimentally 0, but the bounds are small, but not super small. The existence of some new powerful telescopes and the launch of the James Webb Space Telescope in December of this year should lead to more progress on understanding all these quantities. In my view, these are the things that are really important, whereas manned spaceflight is just kind of dumb and dangerous. So if you have a K equals 1 universe, then the universe reaches, for radiation here, a maximum size and collapses back to 0 in a time that's at least 5.6 gigayears for the L that I quoted earlier. A universe of matter, if you have a universe of matter, and now after the first, from 50,000 years to about, I don't know, let us say 9 billion years. So from 50,000 to 9 billion years, the universe was matter dominated. And if you go to the middle of that, it was really matter dominated. And in that case, the Friedmann equations look like this. We said, for some reason, I don't know why I use these crazy abbreviations, m cubed. If we said m cubed equal to 6 pi g Newton's constant, present value of the energy density equal to, well, equal to that, and that's positive. The K equals 0 Friedmann equation gives us root A dot equals a constant. So that's square root of A dA is dt. You integrate that to A to the 3/2 is t. And so you get that A goes as T to the 2/3. So with radiation, you had A going to, so let me write this down. So radiation, A of t, square root of t, matter, A of t, t to the 2/3. And there, if you have a k equals 1 universe, you get a maximum size like that, and then it collapses to 0. The fact that the universe is pretty old, almost 14 billion years, and hasn't collapsed, leads one to suspect that that something like that either k is 0 or negative, or there's dark energy and so forth. And of course, there are many reasons to think about dark energy. In figure 7.5, what we see here is this is a plot of what we think is the correct curve for our universe. And of course, I don't take well, this is in giga-years, so this is a pretty accurate plot. If you only had radiation, it would look like that. And it would increase as square root of t. If you only had matter, it would increase like this, t to the 2/3. Whereas if you add in the dark energy, you have that around this time, the dark energy started to dominate and it increased exponentially. So remember, with dark energy, if that's dominant, then A of t goes as e to the t. And well, since we didn't have any constants in the other equations, I'll just write it as e to the t. So that's the lightning review of cosmology. Now, the equations of physics, let alone particle physics, but t is, well, t is time. And I think it's fair to say that time is less understood than space. In any event, we don't distinguish between time and co-moving time. There's just time, and everything is changing with respect to time. And what we have, I didn't emphasize this, but I did say it a couple of times, namely that space is taken to be maximally symmetric. So I guess that boils down to homogeneous and isotropic. If one looks in terms of general relativity and then considers arbitrary spaces, arbitrary three-dimensional spaces, and adds in time, the arbitrary three-dimensional spaces in general relativity, and now we're imagining that they're curved as you like. And when I think of curved, frankly, what I do is I imagine that we're in a higher dimensional space-time. And in this higher dimensional space-time, you can see that our space is curved. Whereas we are just locked into the three-dimensional space, and we don't look outside and to get a good view of the curvature of our space. In any event, in general relativity, there are only 3 maximally symmetric spaces, three-dimensional spaces. One is flat space, which is obviously maximally symmetric. The other 2 are, well, one is the surface, the three-dimensional surface of a 4-dimensional sphere. And then the other one is basically a hyperbolic space, which I guess is the three-dimensional surface of a hyperboloid in 4 dimensions. Well, anyway, back to particle physics. Physicists normally use perturbation theory or numerical analysis to cope with the nonlinearities. Sometimes they treat the field classically and then deal with the nonlinearity, but of course the nonlinearity itself is not trivial. And so just to show an example, suppose we work in a space-time of just 2 dimensions, and we have a model field theory that looks like this. This is the action density for 2 dimensions, or you can think of it as 4 dimensions, but just nothing depends upon the other 2 space dimensions. And here's the potential energy. This is the action density, or the Lagrangian, and it's the time derivative squared minus the space derivative squared. And Lagrange's equation then is this equation here. And now this is a partial differential equation. Of course, what you can often do is you can convert a partial differential equation to an ordinary differential equation by choosing to say that the field depends only upon a particular combination of the independent variables, in this case, x minus vt. And if you do that, then what you get is a much simpler equation. Lagrange's, well, first of all, the time derivative then is related to the space derivative, not the space derivative. It's related to the derivative with respect to this composite variable. And similarly, the space derivative is just the ordinary derivative with respect to u. And so this equation, Lagrange's equation, becomes 1 minus v squared phi uu, that's the double u derivative, is the partial of the potential with respect to the field. You multiply both sides by the first derivative of the field with respect to this new independent variable u, you get this equation, which you can integrate to that, where E is a constant of integration. If you rewrite this equation, it looks like this. And then if you know what V is, you can integrate this. If you're lucky, MATLAB or Mathematica will do it for you. If not, you can always do it numerically. And then you obtain an expression for an equation involving u and phi. And then you can, in principle, invert that and get phi as a function of u minus u0. Of course, inverting anything like this in general is distinctly non-trivial. But if we go through this example, it's actually possible to carry the whole thing out, because here, this v is a particularly simple form. It's the square of phi squared minus phi0 squared. This is very much like a Higgs potential, by the way. Now the formal solution up here looks like this. It's the square root of E minus V, and I've arranged V so that it has an E in it. And so when we add E to V, this term, which would make the integration more complicated, this disappears. And so we just get this. And that turns out to be an exact integral. It's the inverse hyperbolic tangent. And since it's an inverse function, well, we multiply both sides by lambda phi 0, and we just take the hyperbolic tangent of both sides, and we get that the field of u being x minus vt, is minus or plus phi 0, the hyperbolic tangent of lambda phi 0 times this u variable, u minus u0, basically, over the square root of 1 minus v squared. And these things have been called solitons or anti-solitons. And it's a soliton that is moving along with speed v. And in the figure, I don't know where the figure is. Oh, there's the figure. And so what this is called the kink soliton. And it goes from -1 for negative x, and then it zips up to +1 for positive x. And now the kinetic energy density is essentially 0 once x is, say, greater than 4 or less than -4. All the kinetic energy, everything that happens is when x is close to 0. Okay. I was going to write a section here on MATLAB solving differential equations, and it's easier than I thought, but I didn't get around to writing this up, let's see. No, I don't have MATLAB running now on this topic. I tell you what, tomorrow in the problem session of 468, I will expand a bit on MATLAB solving differential equations. I guess now would be a good time to ask for questions, but also to see whether people would like, let's see, does anybody want to ask a question? Either use the chat or speak. All right, let me go into chapter 8. Let me start chapter 8 then. And this is something that we don't talk about so much in physics classes. We're always focused on differential equations, even though I guess, in a sense, the action that we also often focus on, the action or the Lagrangian or the integral Lagrangian and these various quantities that are conserved, I guess these are all integrals. It turns out that integrating a differential equation leads to, of course, what's called an integral equation. So suppose we have this first order differential equation, du dx is u sub x. That's a nice abbreviation. It's p of x, u of x plus u. Well, we know how to solve this. But suppose we just integrate it. Oh, gosh. Well, if we integrate it, we get this integral equation. And now what is more important, of course, for us is to deal with a second order differential equation, because for second order, we don't have a recipe to solve the equation. So let me just mention. So what one can do is one can use one of Cauchy's identities, and one has to admire these guys, how much they did. And as I said to you before, we find things like this, or Cauchy's integral formula and so forth, and we say, oh, isn't that amazing? That is just scratching the surface. We're just scratching the surface of all the work Cauchy and these other people did. The simple things that they did, the simple tricks that they introduced have become mainstays of modern mathematics. But what they did then was they used all those simple things to investigate problems that at that time were important mathematical or physical problems. And most of us today don't remember or have any knowledge of what it is they were actually trying to solve. Anyway, one of the things that Cauchy did was turn a second order well, first of all, he invented this identity. So the integral of x minus y f dy can be written as a double integral of f. And that's a special case of a more general formula that he introduced, which was that an integral over a bunch of dimensions is those variables, this function f of y integrated from 0 to x dy and x minus y raised to the power n minus 1 to the n minus first power gives you this expression. By the way, in this expression here, what you're doing, you see f is a function of a single variable. So here what we're doing is we're first integrating f of xn up to xn minus 1. Then we have some function of xn minus 1, which we integrate dxn minus 1. And then we have some function of xn minus 2. And we integrate that dxn minus 2 and so forth. And that's the left-hand side. The right-hand side is just a multiple integral of f. I'm sorry, a single integral of f times this funny kernel. This thing is called a kernel. It's the thing that multiplies the thing you know. Or maybe it's the thing you know that multiplies the thing you don't know. Anyhow, so suppose we use this special case and we apply it to this second order ODE. Well, one of the exercises is that you can turn that second order that second order ODE to a very nice integral equation. Yes, all right. So there was a question asked, and let me do my best to God, where are we? To answer the question, if I can find my pencil, then let's switch maybe to green. So one example of 8.4. Okay, so let me do it then here. Let's go from a to x, and then from a to x1, and then I'm going to call that f of x2 dx1 dx2. I think, yes, I think that that's what we want. And so this is going to be, n is 2 here. So I'm setting n equal to 2. And so this is 1 factorial, of course, is 1. So this should be the integral a to x of x minus y, f of y, and this is an ordinary parenthesis here, dy. Okay, so this should be a general formula. Let's see, what shall I do? Shall I, as I said, one can do the exercises and derive this thing. Let's suppose we say f of x is equal to, all right, let's make it really easy for everybody, including me, and especially me. Let's say f of x is x. So this is an integral a to x, a to x1, x2 dx1 dx2. Well, what is that thing there? F of x. Right, I meant x2. Sorry, so hold on, I've got to fix this. So this is x2, right? F of x2, right. Okay, so let's do the integral x2, a to x, then we have dx1 integrate, we have to still integrate. And now what we have is x2 squared over 2 evaluated between a and x1. And so this is equal to the integral from a to x dx1, 1/2 x1 squared minus a squared. By the way, if I'm making a mistake, shout or write in the chat board there. Now we're going to integrate one more time. So we have an overall 1/2. We're going to have x cubed over 3 evaluated here between a and x. Actually, it's x1. And then we're going to have minus a squared times x minus a. All right, so that's the whole business as far as I can tell. 1/2 x cubed over 3 minus a cubed over 3 minus a squared x minus a. And if we simplify that just a little bit, we have plus a squared, plus a cubed minus a cubed over 3. So this is 1/2 x cubed over 3. So that's a cubed minus a third. So that's plus 2/3 a cubed minus a squared x. So that's what I have. I could be screwing it up. Now, what Cauchy says is that's the same thing as the integral x minus y f of x. And so if I can, let me just copy that so I don't, a to x, x minus y, and this is just going to be y dy. So now this then should be integral from a to x of x minus y, y dy. Boy, this is a miracle if this works out. That is x y squared over 2 minus y cubed over 3 evaluated at x and a. And so this is x cubed over 2 minus x cubed over 3. I don't think this is working out the way I had hoped. Minus now I'm a little confused here. Yeah, this is a little bit confusing. This is minus x a squared over 2 plus a cubed over 3. So this is what I've got in this case. Oh, this actually may work because a half is 3/6 minus 2/6 is 1/6. So that's 1/6 x cubed. And then this is minus x a squared over 2 plus a cubed over 3. Well, it kind of works, but it's not really working. So this term is indeed equal to 1/6 x cubed. Oh, and this term multiplied by a half is 1/3 a cubed. And minus x a squared over 2, that is that. So this actually does, let me do it in blue. Why won't it turn to blue? So it actually works. I didn't make a mistake. I thought, as I was doing this, I thought for sure I'd screw up. But that's what this means. And it's, you can see that this guy, Cauchy or Cauchy, was one smart cookie. Anyhow, so what it turns out then that if you use this particular equation, you can integrate this equation well, that's the first order case. You can take this, you can integrate the second order ODE, this thing, you can integrate that into this form. And then you get the solution as u is equal to f of x plus an integral of u of y. Of course, the problem is you have to know what u of y is. So you're not really given a solution. You're just given something this solution has to satisfy. And this k, which is called a kernel, well, it's the known function p of y. These are known functions. That's a known function. So you know everything. And well, f, what is f? So we started with this. What is f? F is a u of a, which is basically a boundary condition, some linear function of x, and then an integral of r, x minus y, and r is this function here. And now you might say, well, boy, that's taking something that was puzzling and making it confusing. But there's something really nice about this. In other words, what you've got here is you've got u, the unknown function, at many points, an arbitrary x, and all the points y between a and x. Well, but that's a linear relation. So what you can do from the point of view of linear algebra is you can just ace this equation numerically. You can just define u as a vector of 10 components or 1,000,000 components, and then require it to solve this equation, and either and you can then I think you can numerically or symbolically do this integral, and then you can use the programs of linear algebra, which basically can do anything, and you can solve the thing. So the point is, it puts it in a form. Integration takes a differential equation and puts it in a form where the other techniques of mathematical analysis can be brought to bear. Whereas if you just are looking at a differential equation, you're a little bit like a rabbit staring at a snake. Okay, well, so much for that. So then there are this section is a lot of definitions, and it's good to hear them once or twice. So an equation of this form with a given kernel, so you're told what k is, and you're told what f is. This is called an inhomogeneous Fredholm equation of the second kind. for the function u and the parameter lambda. Lambda is a kind of eigenvalue. If f of x is 0, then it's called a homogeneous Fredholm equation of the second kind, and that's because it every term is linear in u, and there's no inhomogeneous, there's no non-u term. So now it's a linear equation. Of course, it was a linear equation before, actually. So now this is a homogeneous Fredholm equation of the second kind. And this typically has non-trivial solutions only for certain eigenvalues. And each solution u is then an eigenfunction. So this is what eigenvalue equations look like in integrated form. If lambda is 0, but f is non-zero, then it's an inhomogeneous Fredholm equation of the first kind. So Fredholm's first kind of equation looked like this. Now this right here is frankly just a matrix equation. It's very much like K matrix U vector equals F. So U is K inverse F. So if you write F as an n vector, K as an n by n matrix, U as an n vector, as long as the effective determinant of K is non-zero, you can just do this in terms of linear algebra. Finally, if both lambda and f are 0, then it's a homogeneous Fredholm equation of the first kind. And then that's saying that K annihilates this function u. And they're all, these Fredholm equations we're looking at are all linear. The next topic is the Volterra one. So this man Volterra introduced equations that look like this. And here, let's go back to Fredholm. In the Fredholm case, you have fixed lower and upper indices. In the Volterra case, your upper index is x, and it's one of the parameters in the kernel. And so this is an inhomogeneous Volterra equation of the second kind. This is a homogeneous Volterra equation of the second kind. This is an inhomogeneous because of a Volterra equation of the first kind. And this is a homogeneous Volterra equation of the first kind. And they're all linear. And the Volterra type are basically a special type, a special case of the Fredholm type. And so we're basically out of time. I think on Thursday we can pick up here and study implications of linearity. And what I'll do is be saying in detail what I just said spontaneously when talking with you. So is there a final question that you could shout out or put in the chat box? All right. Let's let me wish you then a nice evening, and we can all go watch the election results. Oh, excuse me. So I'll stop sharing and end the meeting.